Hello future engineers, welcome to my YouTube channel. So here is the first problem. Determine the magnitude and sense of the horizontal force F for which there is impending motion to the right of the lightweight wedge A. Is the wedge self-locking? The coefficient of static friction between all surfaces is 0.15. So this is the given figure. So to proceed to the analysis, we have to draw free body diagram of 400 kilogram block. Remember that the condition is so that there is impending motion to the right. So if this is impending motion to the right, then the friction force between the contact surface between block A and block B would be to the left, and at the bottom also would be to the left. So considering that friction, which is to the left over the top of this wedge, so if we draw the free body diagram of the 400 kilogram block, the friction should be to the right on this bottom portion. So if it is to the right, then the normal should be only on this face here. There will be no normal force here to counter that force of friction which is to the right on the bottom surface of this 400 kilogram block. So because if motion is bending to the right, then 400 kilogram will tend to move down, bending motion also. So therefore, friction here would be up. So the reaction at this surface here would be up to the left, and the reaction at this bottom of this block B here would be up to the right. So this is the free body diagram of the 400 kilogram block. So its weight is 400 times acceleration due to gravity. Then this is up to the left because the block tends to go down, move down, impends to move down when the wedge impends to move to the right as given in this condition here. So the angle that R1 makes with the normal, which is horizontal, is angle of friction, arctan of 0.15, which is 8.531 degrees. So you compute arctan of 0.15. Similarly, the reaction at the bottom of the block should be up to the right, and it makes an angle also of equal to arctan of 0.15 or 8.531 with respect to the normal, which is vertical in this case. So it is with sense because the x component of R1 is to the left and the x component of R2 is to the right. So in order for this block to be in equilibrium. So we draw the force triangle of this block. We had 400 G downward, then R2, which makes an angle of P sub S or 8.531 with the vertical, then R1, which makes an angle with the vertical, this is the vertical, of 90 degrees minus 8.531 or 90 degrees minus P sub S. So this is angle 90 degrees minus P sub S. Therefore, we conclude that R1 and R2 are perpendicular to each other. So they are perpendicular to each other. We are only interested of R2. So R sub 2 is hypotenuse 400 times 9.81 times cosine of P sub S. So R2 is 400 times 9.81 times cosine of 8.531 degrees. Therefore, R sub 2 is equal to 3880.59 newtons. Now we transmit that reaction R2 over the top of this wedge, lightweight wedge here or weightless wedge. So this is it. Then the angle it makes with the vertical is equal to P sub S. And the normal on the underside of this wedge here, lightweight wedge or weightless wedge, makes an angle of, because this is 80 degrees, so the perpendicular to the surface here makes 90 minus 80 or 10 degrees. And because the angle of friction is only 8.531, remember that friction should be up to the left and to the left over this wedge here. So the resultant, therefore, between the normal and the friction is somewhere between these two. Because this is 10 degrees, so R3 should be within this 10 degrees here. So it lies to the left of the vertical. There is still angle, very small angle left because that is 10 degrees minus P sub S. So remember, the angle between the resultant reaction and the normal is always angle of friction. So not considering the force F first, let's solve for R sub 3. So summation forces y equals 0. So R sub 3 cosine of 10 minus 8.531, the very small angle there, equals 3880.58 times cosine of P sub S, which is 8.531. So R sub 3 therefore is 3838.91 newtons. Then, because 3880.58 is greater in magnitude than R3, the x component of R2 is greater in magnitude than the x component of R3, which is to the right. So therefore, because the x component of R3 is very small to the right, it will be resisted by the higher x component of R2. We therefore conclude that even without this F here, even if we remove this F here, this wedge remains at rest. So therefore, to answer the question, is the wedge self-locking? The answer is yes, because even without that force there, this wedge remains at rest. Now, because the condition is there is impending motion to the right, therefore F should be opposite in sense. We need to drag it to the right in order to surpass the x component of R sub 2. There is only impending motion if the force F must be applied to the right, because the wedge is self-locking. So that is summation forces horizontal equals 0. So F plus R3, 3838.91 sine of quantity 10 minus 8.531 degrees is equal to 3880.58 sine of 8.531 degrees. So solving for F, and therefore the sense must be rightward, 477.25 newtons rightward. So that's it, the solution to this first problem. So let's have the second problem. The metal plate A shown in the diagram is fastened to block B by the single threaded screw whose squared threads have a pitch of 1.6 mm. The mean radius of the threads is 6.4 mm. The coefficients of static and kinetic friction for the threads are 0.3 and 0.25 respectively, and friction between plate A and the head of the screw is negligible. The screw is tightened by means of a torque wrench. Determine the clamping force on plate A if the torque wrench reads 54 Newton meter. Letter A, when the screw is about to turn, or we have impending turning, and letter B, when the screw is turning. So when it is turning, then it is no longer the coefficient of static friction that must be used, but rather the coefficient of kinetic friction. So this is the figure, and the formula that we can derive is the torque that will twist or rotate this bolt head here in resisting this clamping force, which is the clamping force here is W. The torque is denoted by C sub O. So C sub O is equal to, remember the formula derived is W, the clamping force, times R, mean radius, times the quantity tangent of the quantity angle of friction P sub S, plus minus the lead angle theta. Then that angle of friction P sub S is used when we have impending motion, and we use P sub K when the screw is turning, keeps on turning the screw. So therefore, C sub O, or couple or moment or torque, is equal to WR tangent of P sub S plus minus theta. So in this case, we use plus because we have to raise supposedly the weight or the clamping force. So we use plus, so P sub S plus theta. We use minus if you're going to lower slightly the weight for that case. Where C sub O is 54 Newton meter, then we convert that to Newton mm so that R, which should be in mm, can be solved. Where P sub S is equal to R tan of 0.3, and it is equal to 16.699 degrees. and P sub k is for part B. We use P sub k, we replace P sub S by P sub k in part B, is equal to arctan of 0.25, which is equal to 14.036 degrees. Then the lead angle tangent theta equals multiplicity of threads divided times pitch divided by 2 pi r. So multiplicity of threads times pitch over 2 pi r, wherein the multiplicity is 1 because we have a single threaded screw. The pitch is equal to 1.6 mm divided by 2 pi, and r is mean radius 6.4 mm. So therefore the lead angle is 2.2785 degrees. Substitute into this formula here. C sub O is 54 Newton meter times 1000. Then therefore the clamping force W is in newtons. So 54 times 1000 Newton mm equals W, R 6.4 mm, tangent of 16.699 degrees plus 2.2785 degrees. Solving for W, so W equals 24,817 Newton. So that is the clamping force. Then for part B, we replace P sub S here, 16.699 by P sub K, and this is still plus 2.2785, and the torque is the same, 54 times 1000 equals W times 6.4 times tangent of 14.036 plus 2.2785 degrees. So solving for W, W equals 28,827 Newtons. So that's it for this problem here. So let's proceed to problem 3. The coefficient of static friction between the disc and the horizontal guide is mu sub S1, and the coefficient of static friction between the disc and the cable is 0.4. So determine the smallest value mu sub S1 for which the suspended block of mass M will not move. So analyzing the free body diagram of this disc here, because the block is the one that has the tendency to supposedly move downward, this is the active force. So therefore the tension attached in the cable to this block here would be the tie tension, and it is equal to mass of the block times G. Therefore the tension on this side here will be the what we call slack tension. This is the tie tension. And during the free body diagram, let's enlarge the figure. So we have the tie tension here, which is equal to mg, and this is the slack tension. Let's just call it T sub S. Then considering this guide here, horizontal guide, summation forces y, so the normal should be equal to mg, and summation forces x, the frictional resistance, so that it will not move, because the question is smallest value of mu S1. So that means we have impending motion for this disc here with the possibility of sliding to the left. So the friction should be to the right, and it is equal to mu sub S1 times the normal, which is equal to mg. So the normal is mg, summation versus y, it is obvious mg, and the friction should be to the right, which is mu sub S1 times normal, which is the normal value is mg. But then summation forces x T sub S equals mu sub S1 mg. That would be the ultimate equation to solve for mu sub S1. So we will express T sub S in terms of mg by the relationship T sub tight equals e to the mu S times beta, where beta is the angle of contact. In this case, we have here the point of tangency at the top, point of tangency at the rightmost point. Therefore, the angle of friction is 90 degrees or pi over 2 in beta there. So tie tension equals T sub S e to the mu, which is 0.4 between the disc and the belt, and the angle of contact is pi over 2 or 90 degrees. So this should be pi over 2 radians in this equation here. So T sub S in terms of mg is 0.5335 of mg. Then finally, summation forces horizontal equals 0, mu sub S1 times mg minus Ts, or equals T sub S 0.5335 of mg. Cancelling out mg, so obviously mu S1 is equal to 0.5335. So that's it for this problem here. Solving for the last problems, all these problems are taken from the book by Ginsberg and Jinin. second edition, Statics and Dynamics 1984. But not all problems are copied. Some of them are, I revised some of the questions, or I revised the data, especially if it is an English unit. If the units are in USCS, so I converted them to SI. And some other givens are also revised. So problem 4, the 80 kilogram square block rests against the vertical wall in the position shown. So determine the largest horizontal force F for which the block will not move if the coefficient of friction between all surfaces is 0.5. So this is the given figure. This is the square block. Then we have dimension B and B here. Then the original problem, the dimensions are given, but I just call it B because the dimension will not change our answer here. So the analysis goes like this by drawing the free body diagram of this square block. And remember that this square block is about to tip over B. The possibility is it will tip over B when there will be no contact at the wall A. Secondly, this block will about to slide to the right when there will also be no contact about A. I hope that you can imagine that. So, in our solution, the free body diagram consists only of the weight, which is 80 times G, then the force F, which is horizontal, the normal, and the friction force at B. So the friction force at B, because motion is impending to the right, would be friction would be to the left, 0.5 of NB. Coefficient of friction 0.5 times NB. So when sliding impends, summation forces Y, then NB equals 80 times G. So this length, by the way, is half of the diagonal. The diagonal is B square root of 2. Square root of B square plus B square is B square root of 2. Then half of that diagonal is 1/2 of B square root of 2, or 0.5 of B square root of 2. Since this angle is 30 degrees, this angle here is 60 degrees, and that's 90. And therefore, because this is the diagonal, and the diagonals are equal, this angle, total angle here is 45. Therefore, the angle that this half diagonal makes with the horizontal is only 15 degrees, 45 minus, because this is 30 degrees. So this horizontal distance is 0.5 B square root of 2 cosine of 15 degrees. That's 15 degrees. Therefore, this moment arm of 80G from B is B cosine of 30 degrees, because this is B cosine 30, then minus 0.5 B square root of 2 cosine of 15 degrees. Then this distance is B, this is 60 degrees, so B sine of 60 degrees. Now, if sliding impends or sliding controls, this normal reaction at B would be equal to 80G, and B equals 80G, and summation forces X equals 0 to solve for F. So F equals 0.5 of 80 times 9.81 times this. Coefficient of friction times NB, 80 times 9.81. So F is 392.4 if sliding controls or sliding impeds first. Then for tipping to occur, then the moment of F about B must be equal to the moment of 80 times G about B also. So F times B sine 60 degrees is equal to 80 times 9.81 times quantity B cosine 30 minus 0.5 B square root of 2 cosine of 15, this horizontal distance here. So we can cancel out B, then we can now solve for F. F is equal to 165.85 newtons. So that's it. That's because this is smaller than 392.4, it means tipping occurs first before sliding. And in fact, there's no way for sliding to occur if we have to compute for the largest horizontal force F for which the block will not move. Increasing that force F will cause the block to tip. So that's the solution, and I hope that you were able to follow the explanation and the solution to these problems. Bye bye and see you for my future videos.